circuit breakers.
So, thank you, Randy.
Okay.
Welcome, everybody. Today, my presentation is on Vibroacoustic, a rapid diagnostic approach for on-load tap changers. So, during this presentation, we will show how the Vibroacoustic method is used as a fast diagnostic tool to easily detect mechanical problems in the tap changers, online or offline, before they create an outage. Over the next 5 sections, we will uncover the full potential of this diagnostic tool and demonstrate the significant advantages it can provide. So 40 to 50% of failures on transformers come from tap changers and are of mechanical origin. These numbers come from Seagray. So 4 studies done by Hydro-Québec, ESCOM, CAA, Australia for 10 years in 3 continents show the same results. And Seagray and IEEE confirmed these numbers. For example, here we have 45% in orange. These are the numbers from Hydro-Québec. So what are the existing methods for OLTC testing? So this table shows a brief comparison between the 5 existing methods presently available in the industry for OLTC maintenance. The Vibroacoustic method offers the widest detection spectrum. This table is from Seagray, and Vibroacoustic is also recommended by IEEE. For example, you can see that overheating and cocking is marked low for Vibroacoustic, but is marked excellent for timing, transition, and arcing. As you can see, the Vibroacoustic method offers the widest detection spectrum since it is able to detect at the earliest stages problems with the brake, selector, lack of lubrication, contact wear, and many other problems related to OLTCs. So how an OLTC works? In fact, we need to move from tap 1 to tap 2. On the left picture, you can see, so we have to move tap 1 to tap 2. How to do it? On left picture, simple changing of taps during an energized status is unacceptable due to momentary loss of system load during the switching operation. On the right picture, the make before break contact concept shown in figure 4 is therefore the basic design for all OLTCs. And the transition impedance in the form of a resistor or a reactor consists of one or more adjacent units that bridge adjacent taps. On the top, you have the reactor principle. So it's a continuous loading. The resistor principle is different. You have 2 resistors, and then we switch to one to the other one. So the idea, in fact, is to transfer the load from one tap to the other without interruption or minimum change in the current load. With an OLTC comprising a diverter switch and the tap selector, the tap operation takes place in 2 steps. Here you have the switching sequence of the tap selector. So in fact, you have 2 mechanisms that could move, the selector and the diverter. So the next step is first pre-selected by the tap selector at no load. Here you have the initial position, and we have to move to the second one. So at the end of the sequence, the switching sequence, the tap selector has moved. So you can see the vibroacoustic recording of the 2 impacts produced by the tap selector. On the top, a zoom of the two impacts. On the bottom of this recording, this is the motor current. switching sequence of the diverter switch. The diverter switch then transfers the load current from the tap in operation to the pre-selected tap. So you can see the impact produced by the diverter and the zoom of the impact. So here on the bottom, the diverter transition, and here it's the zoom of the graphics. Here you have the switching sequence of a diverter switch, so the resistor type OLTC. Here you can see the details of steps of a diverter switch transition from tap 3 to tap 4. The changeover must be made quickly in 40 to 60 milliseconds to avoid overheating the resistance for OLTC resistance type. So we are able to listen to all the impact of the mechanism during a step up or step down operation. Here it's the move of the diverter switch in action. And here you have the different steps that we have to go through to do a switching seconds for the diverter. So motor drive mechanism, this motor allows the tap changer to move from a position to another. So in recording and analyzing the EC or DC current of this motor during the step up or step down operation, we are able to know if the mechanism are forcing or not. The motor current allows us also to start and stop the recording. And usually the motor operates between 2 and 12 seconds. On the bottom, you have the recording current that you can see. You have the inrush current, then what we call a plateau for the current, and then it's the end with a break. And here you have a zoom of the inrush current. So with this, you know exactly that if the sine wave are correct or not. And here you have a picture where you have the EC current clamp, which is installed on the motor. And then, so this way we can record the current. So what is the vibroacoustic methodology? Each operation of any on-load tap changer produces a specific vibroacoustic wave pattern, or what we call a signature or a fingerprint. With a vibroacoustic sensor, which is an accelerometer, we can record the signal exactly the same way a stethoscope picks up a person's heartbeat. And what is important, a stable OLTC always shows consistent signatures. Any degradation of the OLTC induces changes in the signature. So this is the principle of the vibroacoustic. So we have always a reference which we can compare. So what kind of benefits OLTC vibroacoustic diagnostics bring to electric utilities? So a total of 14 benefits have been identified. I present here only 6. First, applicable to any kind of tap changer. Second, use online or offline. Third, quick, easy, and intuitive test, like a stethoscope. The fourth point is that it forces us to better understand on how the tap changer works. And it's excellent in terms of timing and mechanical adjustment. And also it's an excellent tool to help the user to decide which OLTCs are due for a maintenance operation. So what we need. In order to apply the vibroacoustic, the user will need the following equipment: a current transducer, EC or DC, the tap changer analyzer, a computer with open Zen tap, at least one accelerometer per phase with the related mounting base, and the characteristics we will see on the next slides. So here it's an example of connections of Tap 4 Plus, which is the portable instruments. So here you can see the tap glue, where we install what we call the tap base, which is where we screw the accelerometer, and it comes here. Then the EC current or DC current. We do exactly the same connections for an OTMX, which is our standalone monitoring system instrument. So here I have prepared a video where you can see how to install the accelerometer. So I hope it will work. It seems to work. So here, first of all, this is YouTube video to show how and where to install the accelerometer. So first step, we need to identify the tap changer and the motor drive mechanism. So it goes slowly, sorry about it. So here it's the glue. Here it's the mounting base. We identify where to install this mounting base. Then we have to, this is the OLTC. And here it's so now how to install the accelerometer. So you see the guy, which is putting the glue. And here it's the best location for this kind of transformer, for this kind of tap changer. So the next step is to screw the accelerometer and connect the accelerometer tap changer analyzer. In general, we try to do like a loop to avoid any bad manipulation. So this way, the accelerometer will be protected. And here we look for the accelerometer channel input. And it's a simple BNC cable when we are for the current clamp installation. So here you see the guy doing a step up or step down, and you see here the current clamp installed on the motor. And you can see here the tap changer moving. So here it's a real the step up or step down operation. So the recording is done. We get on the bottom the current and on the top the accelerometer signal. Here you can see on the left the current, on the right the accelerometer. It's a new, this could be like a step up or step down. Usually when it's offline, we do all the taps in all step up and all step down. And the guy is simply doing like doing a step up or step down. So if we have like a 30 how to stop it. Okay, so vibroacoustic. So the sampling time, it's the time interval between two readings and is an important parameter to keep in mind. And usually what we do all our vibroacoustic measurement, we use 10 microseconds, so which is a sampling frequency of 100 kilohertz. So here you have an example of good and bad recording of vibration signals. So you have to be careful of this because we have a lot of companies that pretend to do good vibroacoustic, but you have to be careful. Just ask them the sampling frequency. So here you have an example of 10 microseconds sampling time, which is absolutely required for vibration. Exactly the same vibration has been recorded at 100 microseconds, which is okay for timing motion, but not for vibration. And here, just to compare what is a 500 microsecond sampling time, we got a totally broken signal. So in the next slide, you will see the zoom of each part. So here, the 10 microseconds, so you can see like a smooth signal, absolutely clean. 100, the signal starts to be broken, and 500 microseconds, it's totally broken. So you can understand nothing on this signal. It's just noise. Here, the comparison of three accelerometers attachment methods. So with the glue, magnet, and beeswax and measurements results. So here I have received, in fact, a lot of questions regarding the attachment methods and why we use the glue instead of the magnet, which is easier to use. So to answer these questions, we have done recently the comparison of three accelerometers attachment methods. And here you can see the beeswax, the magnet, and the glue. So on exactly the same location, same spot for the tap changer. And so this way we can compare, we have compared the signals. The tap 4 has three accelerometers input and one current input. So it was easy to do, a test very easy to do. So here you have this graph shows a zoom of the impact section of the recording. On the left, you can see the raw data, and on the right, the calculated envelopes for the same data. You will understand what is an envelope, but it's a way of processing the accelerometer signal. So the next slide. So this graph shows the result of the three attachment methods superposed, and we see clearly that glue and beeswax are identical. On the
You muted your microphone.
okay, so
Okay.
sorry about this. So I just go back, or it's okay.
No, it's okay. Just continue.
Okay, so here also I just repeat here, this graph shows a zoom of the impact section of the recordings. On the left, you can see the raw data, and on the right, the calculated envelopes for the same data. You will understand what is an envelope of an accelerometer signal in the next slide. So this graph shows the result of the three attachment methods superposed, and we see clearly that glue and beeswax are identical. So, but for the magnet, the amplitude of the signal is drastically reduced, and an additional impact is introduced that you can see here. On the black signal is the magnet. So you can see that the amplitude is reduced. And when you compare it to the red and the orange signal, it's totally different. The red and the orange are really identical. It's why companies like B&K or PCB, they recommend the glue or the beeswax. And here, but even if magnet is convenient, it has two major problems: the reduced bandwidth of the accelerometer signal and the fact that we lose the location of the accelerometer for the future test, which would negatively impact the analysis of trends. So, but personally, the additional impact is very bad because you have like a distortion of the real signal. Here you have some example of accelerometer installation, and the principle is to put the accelerometer as close as possible to the diverter switch or the selector, and in general we try to put in the middle, so this way if we know that the selector is moving and the tap change and the diverter is moving, so we could get the two impacts, like it's like a mid distance between these two parts of the tap changer. Example of current installations. In the old installation, it's very easy because the motor is apparent, but in the new one, you have to look for in your schematic of your control cabinets to access to the motor drive. An example of test sequence for online tests. So in presence of high voltage, we record operations of one or two taps step up and a step down, or one or two taps. And tests are performed to minimize the impact on the consumers. So for offline test, we record all taps to get a reference. And we recommend to get a reference of each transformer with OLTC of your park of transformers. With these recordings, you could establish your action maintenance plan. So for all your transformers with OLTC, so in fact, you can reach the stage of predictive maintenance because you know which part is going to fail. So Hydro-Quebec envelopes patented in 2001. So on the left, you can see the raw data of an accelerometer signal with the envelope superposed. So Hydro-Quebec envelopes have been patented by Hydro-Quebec in 2001. And on the right graph, you can see the envelopes for the current and the high frequency and low frequency envelopes. So why envelopes? It's simplify the signal, get the shape of the signal, focus on valuable impacts only, easy to analyze, easy to compare, help to detect wear contacts. For example, for the three signals, for the beeswax, the glue and the magnet, the comparison with the envelopes were very easy, but if you try to do the same with the raw data, good luck. So every tap has every tap changer has a specific sequence of operations that can be identified in the envelopes. So depending on the model of OLTC, different signature can be obtained, which are characterized by specific operation length, number of impact, amplitude of the impacts, shape of the current, and so on. So the sequence of operations associated with an OLTC is described in the operation guide provided by the OLTC manufacturer. Most of the times, this guide describes the operation of every single mechanism element acting during the switching operation, such as the diverter, the selector, auxiliary contact, main contacts, and so on. So with this information, the relation between impacts and mechanical parts can be easily identified on the footprints as shown in this picture. So despite its apparent complexity of interpretation, the vibroacoustic method represents a straightforward verification of predetermined repetitive steps. So when you understand your graphs with the envelope, so after you know exactly how your mechanism are working together. Here you have an example of timing chart given by the manufacturer for diverter switching. So this chart explains how and when the transition occurs during the switching of the diverter. So here you have the timing given by the manufacturer. On the bottom right, it's the different impacts. Of course, this recording is zoomed. First, mathematic processing is done by calculating the envelopes for the current drive and the vibroacoustic signals. And at the end of this process, we produced a typical report for each transformer for OLTC. So on the left picture, you can see the raw data, the motor current on the bottom, and the accelerometer on the top. And the diagnosis can be made in 15 minutes for an online test and 1 hour for an offline. When you have recorded these raw data, immediately the software gives you calculate the envelopes and produce an Excel report. And with the dark blue here, the software brings you to some tests, and then after you analyze the signals. And this is the on-site quick analysis. But off-site deep analysis, we use the Excel reports. We have, thanks to the envelopes high low frequency, we're able to detect the contact wear. We analyze the envelopes, and we have also a database where we compare with the OLTC references signatures. Vibroacoustic diagnostic findings. So here you have some examples of detected problems. This one is simple. This is a typical case where the high frequency and low frequency compression give good informations on the degree of wear of contacts. This severe wear contacts, here you have the picture of the mechanism. And before the intervention, more than 60% of differences between the high and low frequency. The high frequency is in red and low frequency is in green. And next slide, you can see that there must be, in fact, the high and low must be almost close together. So after the intervention, less than 20% of difference between the high and low frequencies. So it's the high and low frequency is a good tool. It works on 80% of the cases to detect contact wear, and sometimes it's not. It does not work. Here it's a very quick problem that you can find with only the motor current. Here we can see an example of poor lubrication. It's an unusual shape of the motor current envelope. In fact, here it has to be flat. And if it's not, this means that the current is forcing. We have also examples of abnormal inrush current. Here it's the inrush compression of two inrush currents between two transformers, exactly same type. And the one on the bottom here and on the green signal shows that there was a problem. It was a brand new tap changer. And here it's the current is forcing at the end, exactly like the same previous cases. Here during time, so we can compare the current malfunctions. So here you have some oscillation at the beginning, and here too. So here the inrush is not present. So all these, when you compare all these signals to the typical one, so you can detect problems. Here it's a simple problem also to be detected quickly. It's an example of asynchronism. It's here you see the diverter switch which in normal condition, the switching operation should occur before the current stops flowing in the motor. And in the case illustrated on the left, the switching operation signal is delayed by 120 milliseconds after the end of the current envelope. As it can be easily observed, well, this kind of issue doesn't require the use of reference signature, and the asynchronism can be detected immediately. So, and the intervention in this case consisted in uncoupling the drive motor and adjusting it so that switching operation could occur before the motor current drops. And the figure on the right represents the normal condition of the mechanism after repair. So in this picture, an example of arcing contact is presented. Two tests have been performed on the tap number 10 of the same OLTC. So one test has been performed offline, the red curve, and the other one online, the black curve. By comparing these two signatures, a big difference in the maximum amplitude can be easily observed. In fact, the maximum amplitude of the offline test is HG, while the other one on the online test is 35G. So the image on the right shows the superposition of the two signatures through which it's possible to observe the presence of an extra peak in the online test. So this extra peak represents the arcing contact phenomenon. Vibroacoustic DRM diagnostic. So here detected problems. So here, in fact, what we do, we just add the DRM on the vibroacoustic and the motor current. So by combining vibroacoustic, DRM, and motor current signals, we can easily identify components such as the tap changer diverter, transition resistor, and moving contacts. Analyze the sequence timing of a complete tap change or multiple sequence tap changes. So, and verify the sequence tapping of specific components. Here it's the installation. So you need the tap 4 plus, the DRM accessory, and here the current EC clamp was installed in this example, the accelerometer, and the connections to the transformers offline, of course, because we inject DC current on the transformer. So this is the kind of result that we get. On the top, you have the dynamic resistance, the vibration, and the motor current. So here you can see the correlation between these three signals. And as it can be observed, the accelerometer signature is characterized by 4 main peaks, and the two first corresponding to a specific value of current. And with this, we have used in the first time in the past high-speed video, and these first two peaks have been identified as follows. So the first impact on the first auxiliary contact entering the new tap position, and the second impact of the main contact entering the new tap position, and the two final impacts are not related to the main contacts of the switching taps. Here you have an example of a new Brunswick Power field experience, 1 and 6. So it was in Caracat. They have an OLTC maintenance. It was an MR type M3D 500. And they are on top of Vibroacoustic. They add the DRM, and they performed this test before and after maintenance. Here it's to explain so timing. So you have, it's a complex tap changer because the timing between the motor drives and diverter assemblies is adjusted using the shaft connections between them. So the adjustment is not easy. So here I have used only the main results of this presentation. And here we have an example of bad synchronism before maintenance. Here you can see on the bottom the current for phase A, current phase B, current phase C. On the left, they put two accelerometers, and on the green, they put the current and the voltage that they have recorded from the DRM accessory. And here you can see that the diverter switch for phase A is operating earlier than B, phase B, and phase C. And this is done thanks to the current. So in fact, you can see that this impact is related to this diverter thanks to the DRM, and thanks to the current, we are able to detect the switching operation time and compare it to phase B and C. And after maintenance, so here the after maintenance results now indicate the timing between all three phases and is now better adjusted. And the selectors and diverter operation are now more in synchronization. So here you see, and they operate exactly at the same time. So here they have discovered another thing, but in the down operation, so before maintenance, we are not only seeing that A phase is operating slightly later than the other two phases. In fact, A phase is in operation after the motor current is interrupted. Here I have shown this with the red arrow here, that you have the impact, so which is occurred after the end of the current. And the timing of this diverter is at the limit where it could possibly not operating during a down operation. And this would result in a phase being on a different tap than the other two phases. And here, after maintenance, but in the big improvement can be seen on the down operation where A phase is operating well within the runtime of the motor now, and this aligned with what was seen for B and C. So now you see that the diverter occurs on phase A before the end of the current. So this was solved. Okay, so I think if you have any questions.
Okay. Okay, I do. Okay, let's see. Okay, I found it. Your vibroacoustic approach is used both online and offline, right? How do
Yes.
you decide which mode is more appropriate for different transformers?
It's a good question. In fact, what the wish is, first of all, try to do like on all your transformers, like a recording. And what is to get what we call a reference, and this is done offline. In fact, the offline is like it's your starting point, and then you get all the taps moving. And the online, there is no for the online. In fact, you do an online if you are not able to do an offline. It's simple.
Okay. All right. You've partnered with Hydro-Quebec to build signature databases. How do these reference libraries help your clients feel confident in detecting problems? Can all of your clients access those libraries?
Yeah, we provide like when we provide the software, we have a lot of signatures, references, and some problems. So this way they can help themselves with this library.
Right. Another question, this technology seems fairly complicated. How does Zensol support users who aren't specialists in vibration analysis?
So what we do in general is that we the utility can buy the instruments, do the recording, which is very simple to do and quick because it takes less than 1 hour. And then after, if they are not able to analyze in the first step, we provide three analysis like free. So just so this way they have like a template of the reports, and then after they can learn by themselves if they wish to do this by themselves, or of course we offer the service of the analysis.
Okay, great. All right.
So like a typical way of working, if for smaller utilities, what they do the recording and they send us the results. And then after we provide the reports and come with the recommendations.
Okay, great.